So this is Newton's first law. So Newton's first law has to do with if there is no force, right? So in the absence of force, an object at rest will remain at rest. All that's saying is that forces are what cause things to move. So if there is no force and an object's not moving, it will not just spontaneously start to move. Right? The other iteration of this is an object in motion will continue in straight line constant velocity motion. Right? Meaning that it's a force that causes something to slow down or speed up or change directions. Okay, you may have heard this law as an object at rest tends to stay at rest and an object in motion tends to stay in motion. All right, but this is a little stronger of a statement. Okay, so Newton's second law is really the workhorse of Newton's laws. All right, and it just describes the reaction to a force. All right, so Newton's second law is the reaction to a net force. And it just says that the reaction to a force is an acceleration. All right? So the most reasonable way to write this is this, that the acceleration of an object is equal to the force on that object divided by the mass of the object. Okay, but this is not the way you usually see this written. You usually see this written as force equals mass times acceleration. Right, or F equals ma. But again, Newton's second law is a description of the reaction to a force. So the acceleration is the thing we're observing, and the force is the thing that we're applying. But both of these are equivalent mathematically. It's useful to note that this is a vector equation, right? Force is a vector, and it results in an acceleration. So you can see here that the force on an object causes acceleration in the direction of that force, which makes a lot of sense, right? If I push something in the x direction, it's going to move in the x direction. This also leads us to the units of force, right? So you can see here that a force should be made of a mass times an acceleration, and the mass is a kilogram, and an acceleration is meters per second squared. So a force must be a kilogram meter per second squared, which we define as a Newton, right, which is a capital N for Newton. All right, so this is the unit of force. The SI unit for force is a Newton. Right, and the third of Newton's three laws is this equal and opposite law. So it's just saying that forces occur in pairs. Okay, often we call this an action-reaction pair. And all this is saying is that if object A pushes on object B with some amount of force, object B pushes back on object A with the same force in the opposite direction. Okay, as an equation, that's maybe F12 vector equals minus F21 vector. All right. You may have heard this law is for every action, there's an equal and opposite reaction. Okay, another way to think about this, or maybe one example of this, is let's imagine a coffee cup sitting on a table, right? The coffee cup pushes on the table with some amount of force, right? And that force is due to gravity. And the table, in order to balance that out, has to push back with the same amount of force. So now let's turn our attention to maybe identifying forces on an object. All right, so the first step here is to maybe draw a picture. So I have a list of steps here, but I think it'll be easiest if I just do this as examples. All right, so let's do one example. We'll call it A. All right, and for A, I have a chandelier. Right, and the first step here is to draw a picture. So I'm going to draw a picture of this chandelier. Let's say it's hanging from a couple ropes. Hanging from a couple ropes, and let's say, I don't know, it's a fancy looking thing with tiers. Okay, so that's my chandelier. So identifying forces is fairly simple if you remember that there are only two classifications. There's contact forces and long-range forces. So I just need to isolate the object. So the object that I care about is just the chandelier. And first I'll identify long-range forces. Well, the only one is gravity. Right? And gravity certainly is acting on this. So I'm going to label that, give it a name, so F sub g. Now I can think about contact forces. And contact forces are easy because only things that are touching the chandelier can act on the chandelier. Right? Well, the only thing touching the chandelier are these two ropes. Right? So that's tension, right? And there are two of these, so I'm going to put two of them here. Let's call it, I'm just going to call it T1 and T2, right? And I've identified all the forces now, right? There's only one long-range force, and there are only two things touching the chandelier. So these are our three forces. Okay, so let's do another example. Let's say we have a monkey on a tree branch. Alright, so I'm going to draw a picture. Here's my tree branch. Right, and here's my monkey. He's maybe kicking back, relaxing a little bit. He's got his legs crossed, his arms behind his head, and a smile on his face. So there's my monkey. Okay, so we can identify some forces here. Again, for our long-range force, the only thing we have is gravity. So I'm going to label that as F sub g. And for contact forces, the only thing the monkey is touching is the tree branch, right? If we exclude the air around him, right? So the only thing he's touching is the tree branch. So he can only interact with this surface, right? So if you look back at our list of common forces, 2 of them described interactions with surfaces, right? And that was friction and a normal force. And it seems like both of those would act here, right? If this is inclined, it must be friction that's keeping him from sliding down, right? If this were ice, he would definitely be sliding down. So let's write friction here. Let's say F sub F. And normal force is what's preventing him from passing through the tree branch. So we'll say F sub N. Okay, so that's reasonable. And let's do one more, A, B, and C. Let's say we have a child on a sled. Let's say a child pulled on a sled. Okay, and let's put him on an incline as well. Alright, so let's see here. And maybe it's cold outside, so he's got a little hat on. And I don't know, that looks like a child, right? And let's say maybe there's some rope and another guy over here pulling the rope. Okay? So again, we have a long-range force, it's gravity, right? Gravity is going to be acting straight down, so we'll think about that in a minute. So the long-range force is gravity. I'm going to call that W vector, just to be different. And then contact forces. So we're considering the child and sled as a single object. Okay, so looks like the sled is touching this inclined plane, right? So we have 2 contact forces there. One is friction maybe, and one is the normal force. So say F sub friction and F sub N. And we also have this rope pulling him up the incline, so we also have a tension. We'll call it F sub T. So maybe in the next video I'll address a construct that we can use to start talking about this quantitatively. All right, those will be free body diagrams. So free body diagrams in the next video.